Okay, so today we're going to be looking at non-homogeneous equations. Okay, so we're dealing with second order differential equations, but due to the fact it's non-homogeneous now, it means that we've got a function on the right hand side of our equation. It's not just equals 0. Okay. The good thing is, is that firstly we solve as we would. Okay. So we solve as we would a homogeneous equation. So in other words, the first few steps is we treat it as if it does equal 0 on the right hand side. Okay, which is what we've practiced and what we've seen in the previous lessons. Okay. However, that won't give us the general solution anymore, okay, because there will be a bit on the right hand side. So what that will give us, okay, so rather than getting a general equation at that point, a general solution I should say, we get a complementary function. A complementary function which will denote C dot F. Okay, complementary function. We want to make that bold and underline it. Okay, so previously when it was a homogeneous equation, we would just solve it, get the general solution. Okay, whereas now when we solve it, it's only part of our answer, the complementary part. Okay, so we then have to deal, once we get the first bit, we then have to deal with the right hand side. So we then find a particular solution to the given equation. Okay. Now, that's going to be finding the solution to the right-hand side of the equation. Okay, and what that's called is the particular integral, P dot I, which we've seen used before in other terminology. Okay, so it's very similar to that. So this is called the particular integral. So we want to underline that particular integral, which will denote P dot I. Okay. So we know how to deal with the complementary function part. Okay, we've seen videos on that. How we solve for the particular integral, okay, the right-hand side equation, it depends on what the functions they gave us are. Okay, different types of functions means it will have to have a different type of particular solution. Okay, so that's what we need to just consider just now before we move on. So finding particular integrals. Okay. So what we do is we look at the function that we get given to us in the question. What we do is we choose a function. So we choose a solution of the same form. Okay. As f of x, the function that we've been given on the right hand side. Okay, so we're going to look at a few examples, but we need to make sure our solution looks like the function that they've given us to start with. Okay, and that will give you a clue what we make our function. So there is a few cases to consider. Okay, so let's look at the first case. Okay, so if f of x is a polynomial, function of degree n, okay, then what we do is we try to make our function y equal a polynomial of degree n. Okay, we're going to make sure we match it. Okay, but what we'll do is we'll make it with constant coefficients. Constant coefficients. Okay, so an example would be, okay, that if we had the function f of x equals x squared plus 2x minus 1, okay, so if that was on the right hand side of our equation, then what we would try, okay, we would try our y function to be something with the same power, so cx squared plus dx plus e, with c, d, and e being constant coefficients. Okay, so do you see how that would match the right hand side what we'd be given? Okay, we would just have to solve for c, d, and e, but it would match what that would look like there. Okay, if we had that, okay, what we then do is we then find dy by dx and the second derivative, d squared y by dx squared, okay, and substitute into the equation. Okay, and once we substitute that into the equation by comparing coefficients, okay, so by comparing coefficients of the left hand side and the right hand side, okay, we find constants c, d, and e. Okay, so the idea here is we have to try and match our function, okay, and substitute it into the equation that they give us as our question, okay. But remember, second order, so we'll need to find d squared y by dx squared and dy by dx to substitute in. Once we substitute these things in, the things on the left and right hand side will match with each other, and if we compare coefficients, we can then work out what c, d, and e was. Therefore, we'd work out what our solution would have been for the right hand side. So that's the general idea. You've got to find a function that matches, substitute it in to then get your constants. Okay. So that's the first case if it's a polynomial. Okay. We do get other cases. So case 2. Okay. So what can be quite common is if we get an exponential. So if f of x is an exponential function, okay, so then our function y that we'd match, okay, would equal an exponential function okay, of equal power. Okay, so if the right hand side function was an exponential, we would find, or we would go with a function that had the same power attached to the exponential. Okay, so i.e., quick example, if f of x was 3e to 2x, that means our guess or y function that we want our solution to be, we would try a constant c that would keep the power the same, e to 2x. Okay, then we would do the same thing, we would differentiate it once, differentiate it twice, substitute those in, then we'd work out what the constant c actually would come out to be. Okay, but we would make sure it matched like that. Okay, that's probably one of a more easier one to sort of understand the matchness part of it. Okay, does anyone have any questions at that point there? Okay, so hopefully those two cases sort of make sense about how to match the right hand side and left side. There's a third case, but you've got to be just a little bit more careful with. Okay, so the last case we're going to have a condition for is, let me try it again, that's not right. If f of x is a trigonometric function, sorry. Trigonometric function, then we would try y to equal a trigonometric function. Okay. Okay. So, i.e., this is where the sort of slight difference happens. So let's say we had a right hand side that had equation 4 cos 2x, for example. Okay. Then what we would try is our particular solution. Okay. Well, we want to have a constant, so we'll call it c. Okay, so c cos 2x. But we also need to consider the case if the trigonometric function is also sine. Okay, even though we know we were given a cos as a right hand side. Okay, remember if we need to differentiate our guesses to substitute into our formulas. If we differentiate a sine or a cos, they alternate, they change. Okay, so you've got to consider both types because it might have been that one that was the original. Okay, for the function. Okay, it might have been that, it might have had both parts to it. Okay, so that's just something that we've always got to just be aware of. So every time you see a trigonometric function right hand side, you've got to consider the cos and sine version of it. Okay, do them both. Okay, so that's what our guesses are going to have to be like. Okay, they're the three cases. You're going to get either a polynomial, you're going to get given an exponential on the right hand side, or a trigonometric function. Okay, and those three cases give you an idea on how you go about finding a guess for right hand side and then solving for it. Okay, any questions on that so far? No? Okay, what we'll do is we'll go straight into an example then to show you how this works. Okay, but these questions do take a bit longer. Okay, there's a lot more steps to it now, but let's look at this example. Okay, not example 7, my apologies. Example 1. Got a bit ahead of myself there. Example 1. So, we're going to solve d squared y by dx squared plus 3 lots of dy by dx plus 2y, and it's going to equal 4x plus 4 on the right hand side. Okay, so you can see I've got something on the right hand side now. In this case, it's a polynomial, but it's not too bad. It's not a polynomial of degree 1. Yeah, biggest power on the x is 1. Okay. So what we still need to do is we still solve it as if it equals 0 on that right hand side. Okay, so in order to do that, we get our auxiliary equation. Okay, so the auxiliary equation is, we'll convert these, so it's going to be d squared plus 3d plus 2. And we're solving when that equals 0, okay, because we still need to find the roots for the left hand side. If we factorise that, we get d plus 2 and d plus 1. equals 0. Okay. And if we solve that, it means our two roots are d equals -1 and d equals -2. Okay. Now at this point that told us our general solution. What this has told us, if you remember our notation, is that the first part of our solution, which will be the complementary function part, okay, will be y equals, and we use our two roots, so it's going to be a constant a e to -1x plus b e to -2x. Okay, so that's what we would have been doing last week. Okay, we've got our general solution, but because we're inside, it's just a complementary function here. Okay, but same steps that I've applied. So I've done the first bit, I've done the left hand side. Okay, I now have to deal with my right hand side here. Okay, so for right hand side, which is 4x plus 4, okay, what we're going to do is we're going to guess, okay, for the particular integral that our function y, that was a solution, will have to match that. So it's going to be a constant c x plus d. Okay, so you can see how that will match to the right hand side. Okay. Now what we need to do is we need to substitute that into our equation again right back at the start. So in order to do this, to work out what c and d actually give me, I need to find d squared y by dx squared and dy by dx. I need to substitute in it. I've already got y. Y is cx plus d. Okay, but I need to find these two things, then I can sum in and compare coefficients. So dy by dx. So if I differentiate that, I'm just left with a constant value c. Okay, and if I differentiate that again to get the second derivative, well, I end up with nothing. Okay, it all vanishes. Okay, so those are the data I've got in there. So what I'm going to do is I'm going to substitute that back into my original equation. So my original equation, okay, was d squared y by dx squared. That was the starting off bit. So therefore, sub into equation. So I'm going to get 0. Okay. Then it was plus 3 lots of dy by dx. Dy by dx is just c, so 3 lots of c. Then it was plus 2 lots of y. Y is cx plus d. And that equals our right hand side, 4x plus 4. Okay. Is that step clear on what I've done there, folks? Yeah? Anybody got any questions about where I've plucked those out of? No, okay? Okay. Right. So let's see if we can solve what C and D are from here. So I know that if I just look at my x terms and my constant terms, they should match this right hand side here. So the only the only x term I'm going to have comes from this last bracket here. 2 times cx, okay, so that's going to be 2 lots of cx. Okay. Therefore I'm going to have plus 3c plus 2d, so it's going to be 3c plus 2d. That equals 4x plus 4. Okay. By comparing coefficients, well, I know 2cx has got to equal 4x, so therefore 2c has to equal 4. Therefore that tells me that c is the value 2. Okay, so that comes from the x parts there. Now knowing that, that means that 3c plus 2d has to equal 4. Okay, well we know c is 2, so that's going to be 3 lots of 2 plus 2d equals 4. So therefore 2d has to equal -2, which means that d is -1. Okay, so I found my two constants from a particular integral. Okay, so therefore, particular integral y equals, well, it was cx plus d, so it's going to be 2x plus d which is minus 1. Okay. So this question asks me to solve the equation. Okay, so I now have all the information I've got. So the general solution, okay, to my question so which we know is GS. So G dot S, it's the complementary function that we had, plus the particular integral that we've just solved for as well. Okay, that's how we get our general solution. We just combine both pieces together. So my complementary function, that was A e to the negative x plus B e to the negative 2x plus our particular integral plus 2x minus 1. Okay, so that was the general solution for that equation there. Okay. If I had more data, so if I knew what maybe x, y were, dy by dx were all at the same time, I could then solve for a and b here, but it's still general because I still don't know what these constants were. Okay, so it's a big question, a lot of steps there. Anybody got any questions regarding that example there? No. Okay. Okay. Right. We'll look at another example, and we'll look at one with a different right-hand side to show you how that one works. Okay. So, example 2. Okay, so we're going to solve d squared y by dx squared plus 2 dy by dx plus 2y. And this time that's going to equal 3 e to the negative 2x. Okay, so we've got right hand side which is 3 e to the negative 2x. Okay. So to find the general solution, we're going to have to find our complementary function. We're then going to have to find a particular integral, combine them both together. Okay, so let's start off with our auxiliary equation. So auxiliary equation, d squared plus 2d plus 2 equals 0. Okay, just to let you know that does not factorise. Okay, it doesn't factorise at all. So let's check our discriminant, see if we've got which category we're in. Okay, so b squared minus 4ac, so that's going to be 4 subtract 4 times 1 times 2, which leaves me an answer of negative 4 if I do that. Okay, which therefore tells me I've actually got complex roots. Okay, I've got an imaginary root. Okay, so we need to find that. So, solving these, we'll put it into the quadratic formula. So, minus b plus or minus the square root b squared minus 4ac over 2a. Okay, so that's going to be minus 2 plus or minus, it's going to be the square root of negative 4. We worked out what b squared minus 4ac was, divided by 2 lots of a, which is just 2. So, the square root of 4 is 2, so we're going to have 2i there from the square root. So it's minus 2 plus or minus 2i over 2. And if we divide both of them by 2, we get negative 1 plus or minus 1i. Okay, so there. You can leave it as just an I. You could leave it I. Yeah, that's fine. You could leave it as that there. That does look more mathematical. Okay, you just need to remember that it is just one I because you use that 1 as part of your complementary function. So I've got my data, complementary function. So we're in this category. Okay, then our complementary function becomes y equals e to the negative x. Okay, so that's where that negative 1 at the start comes into, negative 1 power. Then it is a cos x plus b sin x. Okay, there's no numbers next to the x. Well, there's 1, it's just 1 because we've just got one I. Okay, so that's my complementary function. That's going to be part of my solution. Okay, let's now go towards finding the particular integral. So for a particular integral, we will try y equals, so our complementary function was 3e to negative 2x, so we'll try ce to negative 2x. Okay, that's going to be our complementary function there. Okay. So once we've got our guess for what y is, oh, just lost on my page. We need to find the differentials of this. Okay, the first differential and the second differential. Okay, so dy by dx. So if I differentiate that, negative 2 comes down the front, so it's negative 2 lots of c e to negative 2x. Yes, that's going to be the differential dy by dx there. If I want the second differential, then negative 2 comes down again, negative 2 times that negative 2 is plus 4, so it's 4 e to the negative 2x there. Okay, so that's the data that I've got there for my guess. Alright, so doing that, I've missed a c, I knew something wasn't quite right, let's try that again. Still got a c there, so it's 4c e to the negative 2x there. Okay, right, so we need to substitute these into our equation to solve what c was. Okay, so my equation was d squared y by dx squared, so sum into equation. Okay, so it's going to be d squared y by dx squared, which is 4c e to the negative 2x. Okay, then it was plus 2 lots of d squared y by dx squared, which is plus 2 lots of negative 2c e to the negative 2x. Then it was plus 2 lots of y, so 2 lots of ce to negative 2x, and all that had to equal 3 e to the negative 2x. Okay. So the good thing is all our exponentials here are e to the negative 2x, so I just need to work out what goes in front of each of them. So I'm going to have 4c, okay, 2 times negative 2 is negative 4, so it's negative 4c there, plus 2c, so all that would be in front of all my exponentials, e to the negative 2x, so that equals 3e to the negative 2x. So the good thing is here that we end up with just 2c, okay, because the 4c and the negative 4c cancel, so we end up with 2c e to the negative 2x equals 3 e to the negative 2x. So what that tells me is that 2c had to equal 3, therefore c equals 3 over 2. Okay, so that's what my constant c was, it was 3 over 2. So my particular integral was y equals c e to the negative 2x, well it's going to be y equals 3 over 2 e to the negative 2x. Okay. Just lost it again. Come back to it. So, my general solution is y equals my complementary function plus a particular integral that I found. So y would equal e to the negative x a cos x plus b sin x plus a particular integral which is 3 over 2 e to the negative 2x there. Okay, so that would be my solution there. Okay. Any questions? Okay.